Hello and welcome to this webinar on additive layer manufacturing and applications in the military aircraft environment. Our presenters today are Squadron Leader Chris Phipps and Flight Lieutenant John Mercer. Chris is the Mechanical Systems Engineering Authority on Tornado, and John is responsible for in-service engineering on the Tornado GR4's fuel and secondary power systems.
Good afternoon, ladies and gentlemen. I'm Squadron Leader Chris Phipps, and I'm joined by my colleague, Flight Lieutenant John Mercer. This webinar has been designed to provide an overview of additive layer manufacturing, ALM, and provide examples of application within the military air domain. The scope of this webinar will provide an overview of ALM techniques, provide an example of 3D scanning, and demonstrate applications of ALM within the military air environment. It will also look at qualification and certification of ALM components and finally look at future ALM applications within the MAE. Firstly, what is ALM? It's a modern fabrication process that can use a wide range of materials to create products ranging from medical implants to parts of an aircraft wing. The 3D additive manufacturing process is in general the opposite of subtractive manufacturing, where material is removed to reach the desired shape. The process starts with a computer-aided design, which is then sliced horizontally apart to plan its layered-based physical construction. Three-dimensional parts are built up in two-dimensional layers on top of each other as little as 0.05 millimeters thick. Anything suitable for the printing process can be designed by computer, then printed as an actual item, typically by melting powder or wire materials in plastic or metal. This manufacturing process offers great flexibility and opportunities for creating new products quickly at comparatively low costs when compared with conventional types of manufacturing. ALM has received a large amount of press in recent years and is beginning to have a large impact on the way products are developed and made, increasing the opportunities for innovation and providing new ways of carrying out new product development.
This section of the presentation will consider the two main inputs that can produce an ALM output. It is worth noting that the work of the case study detailed throughout this section was completed without charge by Central Scanning, a 3D scanning and printing agency who provide 3D scanning, digitization, reverse engineering and inspection services predominantly to the automotive and aerospace industries. 3D scanning is one of the two main inputs for capturing data which can then be manipulated as required and used as the basis of the physical ALM output. 3D scanning is a fast, efficient process used to collect 3D point cloud data for the creation of three-dimensional models. Each of the millions of data points that make up a single composite scan has its position accurately rendered in 3D XYZ coordinates, meaning that positional data and details from the scan object are captured with great accuracy. The benefits of 3D scanning are already widely recognized within a range of industry sectors, including aerospace, automotive, and heavy industry. 3D scanning commonly aids reverse engineering, rapid prototyping, model making, as well as pattern and component making. The accuracy of the collected data means the scanners can additionally be used for QA purposes, including non-destructive testing and comparing physical dimensions of a component to its drawings. In our case study, you can see here, 3D scanning was used to provide a non-contact, accurate way of collecting dimensional data, which was then transferred to a standard 3D CAD package for additional modification prior to eventual ALM output. Using specialist software, the captured 3D data is processed into a triangle mesh or STL file, which can then be used for a range of applications. As can be seen from the scans of a Tornado GR4, even the finest detail from the scan object is captured. The scanning process requires multiple scans of the object to be captured from every angle in order to create the finished object. Given the way black surfaces absorb RF energy, scanning some areas in this example needed multiple passes, as well as adjustment of the contrast of the software. The scan software is now sophisticated enough to do most of the data stitching without the need for operator input. This is a benefit of this technology as conducting the scans can be carried out by personnel following minimal training. In the military sector, 3D scanning would be useful for capturing damage such as bird strikes to aircraft, and near real-time transmission to the structural engineers who are often geographically dislocated. Raw scan data on its own offers little utility in terms of engineering, as it is simply a facsimile of the original object, and as such, any flaws are reproduced. The data captured from the scan is designed to be easily exportable to CAD for refining, enhancing, or amending the physical model. In this instance, the mounting points of the external stores of the aircraft were significantly strengthened to prevent them from becoming accidentally detached in the physical output. Additionally, the model was completely resized from 250mm to 23mm in length, as required by the intended application. It should be noted that the use of CAD requires significantly more training. Additionally, ALM model data can be created solely in CAD without reference to any external point cloud data. Use of CAD for this application does not differ from the current industry practices, except that the final model is outputted to a 3D printer. This is the finished output. The original model has been scaled down to a precise tolerance and can now be used by industry professionals to create a mould for investment casting. Advancements in 3D printing equipment mean that objects can now be rendered in wax to allow manufacturers to miss out the moulding process conventionally required for investment casting.
So following on from John's part of the presentation, we will look at some of the types of ALM. There are a variety of processes and equipment and materials used in the fusion of three-dimensional objects. ALM 3D printing process tends to be an additive in nature, with a few key differences in the technologies and materials used in this process. Some of the different types of processes include extrusion, light polymerization, continuous liquid interface production, and powder bed. Each process has pros and cons associated with it. These usually involve aspects such as speed, costs, as well as mechanical and appearance properties of the materials, such as strength, texture, and colour. The variety of processes and equipment allow for numerous uses across the private and public industry sectors. Some lend themselves better towards industry use, while others make 3D printing accessible to the average consumer. Some printers are large enough to fabricate buildings, whilst others tend to micro and nanoscale sized objects. Many different technologies can be exploited to physically produce the designed objects. For the purposes of this presentation, we will look at extrusion and power bed ALM types. These are the most commonly used within our area of responsibility. Extrusion deposition, fused deposition modelling. In FDM, the model or part is produced by extruding small beads or streams of material which harden immediately to form layers. A filament of thermoplastic, metal wire or other material is fed into an extrusion nozzle head. The nozzle head heats the material and turns the flow on and off. Normally, stepper motors or servo motors are employed to move the extrusion head and adjust the flow. The printer usually has 3 axes of motion, and a computer-aided manufacturing software package is used to generate the G-code that is sent to a microcontroller to control the motors. Plastic is the most common material for such printing. Various polymers may be used, including polycarbonate, polylactic acid, high-density polyethylene, and high-impact polystyrene. In general, the polymer is in the form of a filament fabricated from virgin resins. There are multiple projects in the open source community aimed at processing post-consumer plastic waste into filaments. These involve using machines to shred and extrude the plastic material into filaments. Additionally, fluoropolymers such as PTFE tubing are used in the process due to their ability to withstand high temperatures. Furthermore, glass and metal may also be used, however they are more expensive and generally used for the production of art and design objects. FDM is somewhat restricted in the variation of shapes that can be fabricated. For example, FDM usually cannot produce stalactite structures since they would be unsupported during the build. Otherwise, a thin support must be designed into the structure, which can be broken away during finishing. In the next few slides, we're going to look at some examples of FDM in the aerospace industry. These examples have been provided to us by BAE Systems. In this slide, you can see the air intake auxiliary door stay has been designed to hold the door open during maintenance and avoid the use of metallic tools which have a history of causing damage to the door. In this slide, the aux-air intake door damper checking tool has enabled a simple solution to enable accurate setting on the maximum and minimum extension of hydraulic piston that was previously undertaken by ruler and eye methodology. In this example, the ECS pipe, the original master part was lost for ECS pipe jig. The FDM part produced from production drawings was used to provide a serviceability way of testing the jig. In this next example, the PTO shaft is a power takeoff shaft that connects the Tornado engine gearbox to the engine. Damage limitations on these items due to their high RPM are critical. This concept was considered to provide protection against damage to the PTO bellows during maintenance, avoiding a £7,000 repair action per part. FDM manufacture process provided a single piece finished assembly with no loose parts. The introduction of these PTO covers were independently reviewed to determine cost savings, and it was reported that this item on its own potentially saved BA Systems in excess of £1 million from preventing unnecessary damage. The ejection seat snatch connector cover is another example of where we've used FDM. The issue was during tornado maintenance, the ejection seats are removed. This leaves the front and rear cockpit snatch connectors exposed. During functional checks, the connectors have to be connected to the stowage position. There were numerous reports of damage being caused to the snatch connectors and cables caused from personnel entering and exiting the cockpit whilst carrying out maintenance activities. The task was to investigate a means of protecting the connector and cable assembly and design covers for both snatch connectors to protect from damage caused during maintenance whilst the ejection seats were removed from the cockpit. In the next slide, you can see the solution to this problem. Utilising the bracket that retains the snatch connector stowage receptacle, a protective cover was designed taking into account variations within the build position and fitment of the bracket. A prototype, as seen in this slide, was produced using the local ALM printer at Royal Air Force Marham. The prototype has a no-step text embossed onto the upper surface, and a recessed area has also been included to accommodate an adhesive part number label. And this final slide shows our 3D printer at Royal Air Force Marham. I believe, though, this is now in the last few weeks as we approach Tornado OSD moved back to BA Systems Wharton. We are extremely fortunate that BA Systems have provided some top-level info on BA Systems Air Sector AM capabilities and have assisted us with this presentation by providing some overview on some aircraft functional parts that have been qualified in the last few years. BA Systems have applied ALM to many other applications, including aircraft protective equipment, ground equipment, tooling, shop aids, as well as aiding spares and repairs. This has been across the full range of AM processes. However, due to the classification of some of these products, we are unable to present on all of them to this audience. The two examples that we will use to provide some examples for the purposes of this presentation have been manufactured using SLM and SLS ALM technique. Okay, firstly, SLM is a particularly rapid prototype ALM technique which uses a high power density laser to melt and fuse metallic powders together. The types of applications most suited to the SLM process are complex geometries and structures. Advantage can be gained when producing hybrid forms where solid and partially formed or lattice-type geometries can be produced together to create a single object. Much of the pioneering work with SLM technologies is on lightweight parts for aerospace, where traditional manufacturing constraints, such as tooling and physical access to surfaces for machining, restrict the design of components. SLM allows parts to be built additively to form near-net-shaped components, rather than by removing waste material. Some of the materials being used in this process can include copper, aluminium, stainless steel, coal black chrome, titanium and tungsten. Generally, for the material to be used in the process, it must be in its atomized powder form. Specific applications in aerospace include air ducts, fixtures or mountings holding specific aeronautical instruments within commercial and military aerospace. In the next slide, we're going to look at a case study of SLM activity in the military aerospace environment. It's the Hawk NACA intake. NACA duct is a common form of low-drag air inlet design originally developed by the US National Advisory Committee for Aeronautics. the precursor to NASA, back in 1945. The original part was of conventional manufacture, welding fabrication from multiple component parts. The issue with this component was that there was a high concession rate, resulting in build shortages and production delays. It was decided that an alternative manufacture approach was required to meet rate requirements, improve build quality and methodology, whilst providing cost and lead time savings. As a result, SLM was considered the most beneficial approach, which resulted in improved design and increased build rates, 36% material and manufacturing cost reduction per component, and a 62% lead time reduction. In December 2015, it saw the achievement of the first fully qualified additive manufacturing metallic component on a customer product, and this was the nacre duct on the Hawk intake. Selective laser sintering, SLS, is an ALM technique that uses a laser as the power source to sinter powdered material, aiming the laser automatically at points in space defined by a 3D model, binding the material together to create a solid structure. It is similar to SLM. The two are derived from the same concept, but differ in technical details. SLS uses a comparable concept, but in SLM the material is fully melted rather than sintered. SLS is a relatively new technology that so far has mainly been used for rapid prototyping and for low volume production of component parts. Production roles are expanding as the commercialization of ALM technologies improves. SLS involves the use of a high-powered laser to fuse small particles of plastic, metal, ceramic or glass powders into a mass that has a three-dimensional shape. The laser selectively fuses powdered material by scanning cross-sections generated from a 3D digital description of the part, as previously described by John, on the surface of a powder bed. After each cross-section is scanned, the powder bed is lowered by 1 layer thickness. A new layer of material is applied on top, and the process is repeated until the part is completed. In contrast with some other additive manufacturing processes, such as FDM, which requires special support structures to fabricate overhanging designs, SLS does not need a separate feeder for support material, because the part being constructed is surrounded by unsintered powder at all times. This allows for the construction of previously impossible geometries. Because SLS can produce parts made from a wide variety of materials, such as plastics, glass, ceramics or metals, it is quickly becoming a popular process for creating prototypes and even final products. SLS has been increasingly utilized in industry in situations where small quantities of high-quality parts are needed, such as in the aerospace industry, where SLS is being used more often to create prototypes for aircraft. In this slide, we're just showing a couple of examples of SLS capability developments. It's got a mixed production portfolio, and SLS has been mainly used for the production of aircraft components associated with the environmental control system, pilot support equipment, and aircraft protective equipment. And the two examples shown on this slide are both parts of the ECS system, one used on the Hawk and one used on Typhoon. The rapid emergence of AM technologies and manufacturers that offer these services creates new opportunities for end users. However, this process also generates a continuous amount of change that could potentially compromise quality and safety. For example, machine suppliers are testing limits to develop higher powered lasers to speed up the manufacturing process. To combat this, a reliable certification system would act as a stabilizing force for quality and safety. Within BA Systems, there are two approaches that have been adopted in qualifying and certifying products: full material and process qualification versus part-by-part qualification. For the SLS nylon-based powder bed ALM process from the example previously shown, BA Systems have a full materials and process qualification that is governed by their own internal processes. For SLM powder bed processes, BA Systems have qualified parts on a part-by-part basis, based on their functional and structural integrity. Data is still being gathered that will in time form a material specification, but to enable BA Systems to move forward and harness the technology for low structural items, this was considered an extremely positive way forward. Parts that are currently qualified on military aircraft, shown in the previous slides, with a nacre inlet duct, and this was using SLM solution, and the Typhoon ECS ducts use SLS nylon solution. BAE Systems have applied ALM to many other applications, including aircraft protective equipment, ground equipment, tooling, shop aids, as well as spares and repairs. This has been across the full range of ALM processes. Looking ahead to future developments, it's important that we touch on industrial digitalization, Industry 4.0. At its simplest, industrial digitalization is the application of digital tools and technologies to the value chains of businesses who manufacture things where technologies enable the physical and design worlds to be merged. Industrial digitalization technologies, IDT, can bring significant enhancements to performance and productivity. These IDTs come in various forms and various levels of maturity, ranging across artificial intelligence, the Internet of Things, robotics, and analytics. Together, they are driving what is called the Fourth Industrial Revolution, Industry 4.0. Industry 4.0 is very much upon us. It is characterized by a fusion of technologies that are blurring the lines between the physical, digital, and biological spheres. What distinguishes this revolution from its predecessors is the speed of technological breakthroughs. In fact, the World Economic Forum has shown that when compared with previous industrial revolutions, Industry 4.0 is evolving at an exponential rate, and ALM is very much part of this Industry 4.0. In the next few slides, we'll be looking at future developments, but it is important that we touch on industrial digitalization. Industry 4.0, at its simplest, the industrial digitalization is the application of digital tools and technologies to the value chains of businesses who manufacture things where technologies enable the physical and digital worlds to be merged. Industrial digitalization technologies, IDT, can bring sufficient enhancements to performance and productivity. These IDTs come in various forms and various levels of maturity, ranging across artificial intelligence, the Internet, robotics, and analytics. Together, they are driving what is being called the Fourth Industrial Revolution, Industry 4.0. And it is very much upon us. It is characterized by a fusion of technologies that are blurring the lines between the physical, digital, and biological spheres. What distinguishes this revolution from its predecessors is the speed of technological breakthroughs. The World Economic Forum has shown that when compared with previous industrial revolutions, Industry 4.0 is evolving at an exponential rate, and ALM is very much a part of Industry 4.0.
Although analysts still consider the additive manufacturing market to be a niche sector, they nonetheless state that it had a volume of £2 billion in 2012. It took the sector 20 years to reach this value, but the second billion was attained only 5 years later. And analysts now believe that it could grow at least fourfold over the next 10 years. Given the cost of equipment and print media, as well as the limitations of print speeds, ALM is primarily used for rapid prototyping or low-volume, high-detail products, whereas machining and injection molding are predominantly used for high-volume, mass production lines. Segments of the industry are predicting that as 3D printing processes become more efficient, ALM may be utilised for some of this high-volume work. Supporting this assertion, Siemens predict that ALM costs will become 50% cheaper and 400% faster in the next 5 years, which may in time make it a more financially viable option. Having researched this area in order to deliver this webinar, I personally see no compelling reason to switch from conventional manufacturing to ALM in the short or medium term for high volume and low variety production lines. ALM's greatest utility is its ability to produce complex shapes accurately and without the requirements for moulds. I believe that this switch to high volume ALM manufacturing will only occur when the advantages of additive manufacturing technique in terms of material usage provide a significant cost benefit when compared to conventional reductive methods. Instead, I believe we'll see greater use of ALM in customized, low volume or high complexity applications. Customized applications will include personalized parts for use in medicine, such as prosthetics or dental work, where a slight variability is required to personalize the item to the user. Similarly, use for small batches removes the need to incur the expense of making molds, whilst use in high complexity applications will allow items to be created that couldn't previously have been used using traditional techniques. The ability to be able to create complex parts using techniques not previously available will remain the main aviation application in the short to medium term. ALM will be used for alloys, precious metals, and for products in which different sections are printed with different materials. Such products could include a material that provides heat resistance and another for ensuring stability. Moreover, metals that melt at high temperatures could be used in completely new ways. As a result, it would be possible to quickly produce exact and customized replacement parts on site when they are needed for individual aircraft or entire power plants. This would not only eliminate storage and transportation costs, but also save money by preventing downtimes. An example of where this technology is already being used in this way is Siemens burner tips for gas turbines. Being able to repair existing gas turbine combustion chambers by printing a new tip on reduces the repair time for certain models by around 90%, because the replacement part no longer has to be laboriously welded together. Instead, the burner tip is simply printed onto the body of the burner, reducing repair costs considerably. In the long run, further work is likely to be completed to allow ALM in metal to be used to produce some of the primary and secondary structure to be manufactured for the aircraft. Here, the weight-saving properties offered by ALM will be enormously beneficial to aircraft manufacturers and operators. The necessarily intensive clearance process requires a body of evidence. A product made by means of ALM manufacturing could cost 10 times as much as a conventional item, but would represent good value if consistently reduced fuel consumption by 1% during the component's entire service life. The challenge for the next 3 to 5 years will be to identify the components for which this equation is valid.
So some of the future considerations, some of the key challenges in ALM future developments are material process. We need to further establish confidence and consistency in material supply, considering processes, variability and repeatability whilst continually seeking alternative material applications. Standards, regulation and certification. Currently there is a lack of standardization in the ALM industry, with further regulation and clarity required in material supply chain. In addition to this, we need to continually gather evidence to further support qualification and certification of these parts. As engineering ambassadors, we all have a responsibility for the continued development of skills education and awareness. This includes process understanding and training. BAE Systems have undertaken some significant work in this area with Cranfield University. Undoubtedly, in the advancement of ALM, it will continue at an exponential rate. And as engineers, we will need to consider the use of ALM in determining our solutions to engineering issues in the future. In summary, compared to conventional manufacturing, the general advantages of ALM are the capabilities in design and development of products. The ability to produce highly complex parts without tools whilst gaining a decrease of production costs is wholly achievable. By its nature, ALM is well suited for low volume production. Hence, affordable and high-complexity individual products can be manufactured. Due to the differences in ALM compared to conventional manufacturing, the follow-up processes for a manufactured product's quality are different. In order to provide a basis for future certification activities for ALM technology, it is important to collect and analyze information related to established production steps for ALM parts, particularly when considering qualification and certification of primary and secondary aircraft parts, as ultimately this determines a product's quality. Ladies and gentlemen, John and I would like to express our thanks for your interest in our presentation, and I'd now like to invite you to ask any questions.
Thank you, Chris and John, for a great input there. Let's just sorry about that. Let's go to questions. The first question we've got is: are you mainly using plastic or metal parts?
Hi there, it's Chris Phipps on the line here. So from the examples that we've seen that have been used, so the majority have been for plastic parts, so the nylon based, because these have offered us a very quick and easy solution for off-aircraft components. But the ducts as well, you'll see that there are some metal applications that are being considered.
Okay, that's great. And is there a need to do much post-processing?
Yeah, so certainly it depends. So it depends which channel you go down to create the pattern for the part. So from the scanning side, which is something I got acquainted with during the research for this webinar, absolutely, because as I mentioned, the 3D scan is literally a facsimile of the original object. So it picks up any flaws, and therefore the scan itself offers little utility. Now, if you're designing from CAD, and then obviously the item that you draw should be in its finished state, as per any conventionally manufactured reductive part.
And just following on from that, so that's post-processing on the after you've scanned it. Is there post-processing needed after you've manufactured the part using an ALM process?
So from the examples that we've seen, there is some finishing off of the component once it's come off of the actual 3D printer, but these are just sort of like very small marginal finishes.
There can also be, depending on which process you use, there can also be a requirement to use like exposure to UV as well to finally set the polymer.
Right. Okay. So another question from one of the listeners is, how quickly can you go from a shape to be scanned to a final part that you can use?
Well, I think with that one, it all depends on what the part is and what its application is. But for some of the off-aircraft components, it was a matter of weeks from getting that scanned and then printed. I think some of the on-aircraft applications have taken slightly longer. But like I say, it's the ability to rapidly carry out any sort of prototypes, which is the distinct advantage of using ALM techniques.
Great, and we've got another question, which is, what is the consistency of quality across a batch of identical parts?
Okay, again, it depends on the techniques being used. So in investment casting, which we looked at for this, probably 1 in 5 parts could have a defect or a flaw. It depends on the cross-section of the part you're printing. But that's mostly errors that have come in from the casting process rather than the 3D printing process. In 3D printing, it depends how you print, because if you print a batch up as one go, so as one run of the printer, then you should have a very low rejection rate.
Okay, so the next question is, have you found any value in printing parts or spares for aircraft positioned overseas where delivery lead times could cause an issue?
I've not got any examples of that to hand, but yeah, it would be a very positive way of getting something printed out so we could send it overseas to avoid excessive lead times.
So we've seen, obviously, the example showed Siemens using their burner tips, which I suppose is a variant of that. But again, as we mentioned, the biggest advantage we see at the minute, because obviously Chris touched on the necessarily intensive qualification process, the biggest utility we see at the minute, certainly from the scanning side, is the ability to convey damage to design engineers, that are geographically dislocated. So I'll give you an example. At the minute, if we get a major bird strike that goes on to the level of structural repairs required, we send all those measurements in by using very old-fashioned methods, and a lot of the dimensions will be worst case, best case, or the lowest point, or the greatest point of impact. With 3D scanning and the ability to rapidly print at the other side, you can give a direct facsimile of that damage to an engineer, and then they can come up with their own repair based on that and the original drawings. I think that's probably the closest application that we will see in the next 5 to 10 years.
Okay, so we've got another question, which is, while FDM has a well-known anisotropic weakness to layers shearing, have you encountered any strength problems with in-service components, e.g. with sintered powders and vibration loading?
I've not had any of that information given to us by BA Systems. Obviously, they go through their qualification aspects on a part-by-part basis. But certainly from the FDM applications that we've used from an off-aircraft perspective, they've been relatively, reliable. each and every time. I mean, I could certainly ask the question if they've had any further examples of issues with some of the stuff they've printed, but I would have to forward that information on.
We did, some years ago, we did design some covers using FDM for some avionics equipment. And we did notice a little bit, so we noticed brittleness was the biggest problem with them, but obviously we would use material and construction processes appropriate to the application, so we would never use anything with anisotropic weaknesses in any sort of critical application.
So, and I guess a related question to a degree, what material properties did you use for the flying parts, and what fatigue properties did you use within that?
So again, the components we've made on aircraft, so that fly with the aircraft, have no inherent structural purpose. So probably the closest we can come to anything with structural integrity would be the running guards for the shafts. So the cross-drive shafts that take power from the gearbox to the APU and across to the other gearbox. We use those as debris guards. So we've gone for toughness as the material properties over any load-bearing capability.
Sorry,
well, in terms of fatigue, so obviously fatigue properties, we monitor, so for certain parts of the airframe, we monitor the fatigue index. But when it came down to an ALM part, that would only be used once. So the running guard for the shafts was, for that one critical application, we wouldn't measure fatigue, wear or count on that item.
Okay. Can you use additive for repairing parts?
Yeah, so the Siemens burner tip, so that's a great example. So in the combustion chamber, so rebuilding parts of the combustion chamber rather than creating a new combustion chamber is certainly a great example of where it's being used now. It's not used on the Tornadoes RB199 engines at the minute, but they're an old engine and we're going out of service. But going forward, I'd expect to see more applications of items being recovered rather than the creation of new items.
Okay, and another question is, you didn't mention anything on the attractiveness of ALM for the potential for drastically improving buy-to-fly ratios of parts when compared with those manufactured using classical subtractive techniques.
Sorry, can you repeat that question again, Ian?
Yes. So it says you didn't mention anything on the attractiveness of ALM for the potential for drastically improving buy-to-fly ratios of parts when compared with those manufactured using classical subtractive techniques.
Yeah, I believe that we touched on in the presentation about the ability for it to deliver rapid prototypes. There is a significant reduction in build times and also a reduction in waste as well when we're manufacturing ALM parts. I only see that there's great future benefit in part applications in the future. Whether we start using these for primary and secondary structures obviously then introduces additional complexities associated with stress and fatigue loadings on those parts. But yeah, there's huge benefits in using ALM applications.
And we've got another question here, which is, can this technology be used for food printing, maintenance equipment printing in space and construction of buildings?
Yeah, I mean, that's quite a wide-ranging question, but certainly the food one, any avid One Show viewers will know that they've recently featured food printing. I mean, it's quite a universal technology. So food, yes. What was the next part of the question, sorry?
So it's food maintenance equipment printing, and it was space and construction of buildings. So obviously we're not maintenance equipment in space.
Yeah, we're not expressing those fields, but I should imagine that 3D printing in space will be one of the key tenets of achieving, all their objectives that they have planned. So I would assume so, but I can't comment on that. And certainly for printing off maintenance machine parts, yeah, absolutely. I think commercially, that's where it's going now. So with 3D printers, one of the interesting things we saw during our investigation into this webinar were printers where they could auto-switch the filaments or the materials used to create the item, so no longer are we trapped to a simple FDM part printed in one colour. We can use multiple different materials now, and I think as that utility increases, that's where we'll start to see, printing out spares for our Dysons, as I think industry envisages that's the path we'll go down.
Okay, no, that's great. Now, we're getting to the end of our questions, so if any of the audience have got any questions they'd like to plug in, please do that while I ask this question. As you look forward and into the use of structural parts, how long do you think it will be before we're going to be regularly seeing structural parts flying?
So this is Chris Phipps's opinion. So I think probably within the next 5 to 10 years, in my personal opinion. Obviously, we've got new aircraft that are coming into service, and again, with those, the introduction of those aircraft, the companies that they're designed by have specific requirements. So we haven't got the immediate ability to carry out modifications as we would particularly on a legacy aircraft. So that is one kind of constraint for us. But again, with ALM in general, I can only see it growing exponentially in the future.
I think the buy to fly argument will be the tipping point when you think of how much fuel you can save just by using ALM designed structural components. So we saw a company who predominantly provide services, so printed in metal, to the Formula One industry, and they had some test components that had about a third of the weight to them as the component they copied from, but structurally were offered as much structural benefit as the original components. And I think that the argument for clearance will be made probably through commercial airlines. I think military will probably ape commercial, and we'll probably give them maybe a generation of aircraft to get that argument right before we start to use it in the more critical application of certainly in terms of military kinetic delivery.
Okay, great. We've got a few more questions now. If all in-service parts are non-load bearing, was the use of sintered metal, e.g. on the intake duct, a choice based on heat resistance? Could high temperature polymers such as PTFE also be used in these applications then and provide a weight and energy saving?
Sorry, could you repeat the second part of that question again, please?
Yeah, so could high temperature polymers such as PTFE be used in these applications, providing a weight and energy saving, for example, such as the intake duct?
Yeah, I wasn't involved directly with that modification of that part, but yeah, I don't see why it couldn't, because it's in a relatively low temperature environment, but it was considered at the time by the company to be the best fit for what they required.
Okay, great. And another question is, are there any benefits from a procurement point of view in terms of securing raw materials?
I'm not quite sure what Gareth means by securing the raw materials. Do we think he means the raw materials for actually the ALM creation?
Well, why don't we move on to the next question and ask Gareth to send in another question that explains it. So are the RAF utilising their unmanned air platforms as test beds for AM parts?
No. So although there may be the inclusion of AM, and again, I'll stress that we're Tornado engineers, obviously our unmanned aerial vehicles still have that same criticality, even though there's nobody in the cockpit. Actually, in terms of the risk to life and the seriousness that we give the argument, it's everyone below the aircraft. So I would think that we would accept no more risk on our UAVs, and therefore we'd only stay in line with what's currently cleared, and I don't believe we've cleared any structural components, so no.
Yeah, and in addition to what John's just said, we remain accountable for third-party risk to life for everything, so that includes the people that we fly over and operate over. So, yeah, no, we wouldn't take any reduction in risk. Okay,
no, thank you. What are the size limitations on our ALM components and subsequent printed beds? Is it potentially aimed at smaller components, or can it be used on larger parts too?
The size all depends on the size of your printer that you've got. I don't think there's any limitation into the size of what you can print out. It just depends on the actual hardware of equipment that you've got there and then.
I think now we've got people like Siemens and GE looking very closely at ALM. We're seeing some really big industrial printers, so I think commercially, I think size won't really be a factor. Obviously, a lot of our components are composite in terms of the fact they're made up from several different assemblies bolted together, so that always remains an option.
Okay, and another question is it new startup suppliers providing ALM, or is it existing manufacturers who are branching out into ALM? How much technical experience and support do current suppliers have to assist engineers?
I mean, that's a really interesting question. So we encountered a mix of both. Obviously, a lot of the evidence that Chris used came from BAE, who are established and have branched into it. But a lot of the scanning and capture companies and the NDT side of things are new companies that have seen a gap in the market and branched out into it, which obviously brings benefits and disadvantages. But the benefits are that these are people that are looking at the industry with a new set of eyes and are looking at ways that they can achieve their end outcome, whereas we may not always get that from established companies who are effectively trying to do what they used to do and just using different technologies. So we've seen a mix of both.
No, that's excellent. We've run out of questions, so if there are no more questions, and if Chris and John, is there anything else you'd like to add before I pull this to a close?
Just really like to thank everyone at the IMechE for their help and assistance in putting this webinar together. Thanks to yourself, Ian, for doing a great job chairing. If anyone has got any other questions that they would like us to answer, then just go via the IMechE. They've got our contact details on there, and we'd be glad to offer any assistance. Okay,
no, that's great. We do have. Apologise, we have got one final one through. Do you think that the use of AM techniques could result in redesign of future aircraft components? If so, what kind of improvements would we expect from a function-driven design compared to conventional design?
I think really, again, it will be the time saving, so lead time on components, obviously savings that you'll make from a lack of, so reducing the waste from that you would normally see in conventional manufacturing techniques, weight saving, etc. I think the limits are endless, really.
I think it'll occur, in at the same time, so concurrently with things like moves into UAV, where we don't necessarily need the same considerations with regards to keeping aircrew alive. So I think we'll see that aircraft design change anyway in some applications, and I think that ALM will go hand in hand with that. So we've seen that using ALM processes, when they design a structural component, it's all built up in a geodesic structure. So although the basic form is the same, it's the internal workings that are different. So I don't anticipate we'll see any sort of aesthetic changes in the short term.
Okay, that's great. Well, with that, Chris and John, I'd like to thank you for really excellent input. I'd also like to thank all the attendees of the webinar for their questions and for their attention. We do hope that we'll see you at future webinars. I think we're seeing more and more really interesting webinars coming through the IMechE, so it's definitely something to watch. And with that, thank you very much, and I'll draw the webinar to a close.
Thanks very much, Ian.
Pleasure.